So remember that the derivative is the limit of average velocities as the denominator goes to 0. Okay, and this is closely related to two geometric objects, which are the secant line and the tangent line. The secant line is very closely related to average velocity, and the tangent line is very closely related to instantaneous velocity. So let's write the definition of the derivative again. So remember, the derivative of f at x is the limit, as h goes to 0, of f at x plus h minus f of x over h. Now let's ignore the limit for a second, all right? If we just look at this expression for some concrete value of h, then that is an average velocity. For example, if h equals 1, then we have f at x plus 1 minus f of x over 1. Okay? That is the average velocity of the function f over 1 unit time interval, over a 1 unit time interval. What would that look like? Well, let's look at the graph of a function f. Let's just say it looks like that. Okay, and let's say, just to be concrete, that x equals 5 in this situation, h equals 1. So maybe this is 5. All right. What we're looking at precisely is f of 5 plus 1 minus f of 5 over 1. And in fact, when you divide anything by 1, you get the same thing back. So this is just f of 6 minus f of 5. Here's f of 6. F of 6 minus f of 5. So this quantity, this average velocity, is just this distance. All right? Now let's do this with a very concrete function. Let's look at f equals f of x equals x squared. Let x equal, let's say, 2. Let h equal 1/2. What is the average velocity for h equals 1/2? That is, again, we look at this expression, f of 2 plus 1/2 minus f of 2 over 1/2. Now we know our f is concrete, so that's 2.5, let's say 2.5, squared minus 2 squared over 1/2 equals, this is just 5 halves, right? So that's 25 over 4 minus 4, and I'm going to bring this to the numerator, times 2. So this is 6 1/4 minus 4 times 2 equals 2 1/4 times 2, which is 4 1/2. Now let's draw what we've just computed. This is the slope of some line, but which line? This is the slope of the secant line between the point 4, 2, x is 2, 2 and 4, and 2.5, I'm going to write that as 5 halves and 25 fourths. All right, so here's my x squared function. I'll make my 2 maybe here, 2. This isn't drawn well to scale, but it doesn't matter. So here's my point 2. Here's 5 halves, 2.5. And here's my value, 25 over 4. And there is a line connecting these 2 points. This is the secant line. Okay. And this is the slope of this secant line. Now remember, the slope of the secant line is an approximation to the slope of the tangent line. What we really want is the slope of this line at 2. And you can eyeball it and see that it's slightly lower. The slope of this line is smaller than the slope of this secant line. But you don't know how much smaller yet. You have to use the derivative to compute the slope of what is called the tangent line, which is this line right here. Okay, so the slope of the tangent line is when you take the limit. This limit. So let's do it. We're going to use the same numbers and the same function. Again, we have f of x equals x squared, and we're interested at the tangent line at x equals 2. What's the slope of the tangent line? Now we take the limit. It's the limit as h goes to 0 of 2 plus h squared minus 2 squared over h, because that's the definition of the function, is limit as h goes to 0 of, now I have 2 squared plus 4h plus h squared minus 2 squared all over h. The 2's cancel, the h's cancel, and I have the limit as h goes to 0 of 4 plus h. And now I can just plug in h equals 0. There's no problem with dividing by 0. And that just equals 4. So notice how similar the values are. For the secant line, in other words, the average velocity, this is average velocity, I got 4.5, and for the instantaneous velocity, I got 4. Let me write that down. Average velocity is slope of secant line instantaneous velocity slope of tangent line.